presentation is based on the project we did for peer, and it was complete 6 months ago. And my student, Hamid Taqavi Ganji, worked mainly on this project. And basically in this one, we wanted to give a try to machine learning and see how good it is in helping us accelerating many task queries in problems related to solid structure interaction. The problem setup that we defined for this project was considering the buried structure in a soil deposit which is subject to earthquake wavefronts. And if you want to solve this problem numerically, one approach to use is the domain reduction method, that we can replace the original problem with a two-step problem that in the first step we try to solve a background model. So either analytically or numerically we compute free field responses that we don't have that localized heterogeneity like the buried structure here. And after computing the free field responses like U0 that I've shown in these equations, then we can compute the effective forces that we can define as one layer, one element thickness layer here, like shown as a red color, to derive the actual problem in the second step. So in the second step, then we are solving a scattering problem that we have that localized heterogeneity involved, here the buried structures, and then we can compute the responses. So for the scattering problem, then of course we have outgoing and propagating waves coming from that structure, so we need to absorb that, and for that we can use different types of absorbing boundary conditions. So here I'm showing an example of using perfectly matched layers. On the right you see the results of some of the simulations that we can do by using this methodology. And we wanted to see if we can replace that with a surrogate model that still we can predict the response of the buried structure. But we wanted to start simple, and for that we assumed that as a first step everything is linear, so we didn't consider any nonlinearity in soil or a structure. But, and also we assumed that we can replace the earthquake wavefront, which is three-dimensional, by inclined plane waves. So in order to characterize the incoming waves, what we need to do is the time history of that event and also the angle of incidence. So this is how we characterize the waves that are reaching the structure. On top of that, we wanted to have some uncertainty in our system properties. And for this project, we assume the depths of the tunnel or buried structure and also the soil properties in terms of depths, varying shear wave velocity to be the source of uncertainty or variability. And for modeling the shear wave velocity or VS profile, we assume that is going to change with depths using this function that we have three parameters, VS0, K, and N, that we can change, and based on that we can get a different realization of that depth varying VS. Then what are the quantities that we are interested in? So we wanted to give a try and see if we can have a surrogate model that can, when we have these sources of uncertainty and input features, how we can predict the response in terms of, let's say, displacement time history at different locations on the buried structure. And for example, here I'm showing 20 positions that we wanted to predict the response in both horizontal and vertical direction. And if we have that one can imagine that, okay, we have two displacement motions, displacement at the bottom and top, and we can compute the racking if someone is interested, which is one parameter that we usually use for buried structures to get their performance. So, so that is the problem we have, and one approach that we usually use to make these analyses faster is the physics-based reduced order modeling approach, that we replace the surrounding soil with a set of spring models, and then we try to use either free field motion or some modified motion to excite these springs and get the response of the buried structure. But in many cases we need to make lots of simplifying assumptions to be able to do the analysis. And not necessarily these spring models and input motions are ready to use. And because of that, we may introduce lots of error and bias in our predictions. So because of that, we wanted to see if we can use machine learning, and more specifically long short-term memory recurrent neural net to predict the response of these buried structures. So here I'm showing kind of the big picture of this model. I don't want to go to the details, but I wanted to emphasize some key features of this proposed model. So first of all, we wanted to ensure that we can accommodate both time-dependent and scalar random variables as input. So now, as I mentioned, we have the plane wave, and we wanted to make sure that we can change the time history of that plane wave, and on top of that, the angle of incidence, shear wave velocity, and depth of burial are another source of uncertainty we have, and we wanted to make sure that we can give both of them as an input to our model. Another thing that we tried was to see if we can avoid selecting earthquake to train the model. So what if we can use synthetic data for training and then test that for predicting the response under earthquake. And also, in order to make our training as efficient as possible, we wanted to also try short duration synthetic time history. So that was what we wanted to try. We also used some static approaches to make the model even more efficient and accurate. So, and that was something that proposed in previous studies as well. So this is kind of the main features of the surrogate model. And then, of course, like any machine learning, which are based on data, we need some labeled data. So I talked about that numerical approach. We can use that to generate our labeled data. And for all the simulations that we did, we used the Sizemore VLab, which is open source finite element code that has the domain reduction method and perfectly matched layers implemented. So that was the model that we used. And for any combination of input we have, we compute the effective forces, and then we can compute the response of that buried structure. Then the question is that, okay, we want to use the synthetic data and short duration one, but what type of synthetic data? So we gave try to harmonic and also Ricker wavelet, but these are usually a very narrow band excitation, and not necessarily they can reproduce the response to broadband excitation like the earthquake. And then we tried the white noise, and we noticed that if we have realization from the white noise, since it is broadband enough, then we can successfully predict the earthquake response. So that was our choice for the synthetic data. But we did some processing on that. So when we have the white noise, then we pass it through some filters to ensure that its frequency content stays in the main region that our earthquake time histories are going to have frequency content. So as I'm showing here, we filtered our white noise to have the frequency between 0 and 15 to 20 hertz. So then here I'm showing kind of how we generate our label data. So for instance, let's say that we have the angle of incidence and the shear wave velocity as random variables. We can use Latin hypercube sampling to generate different combinations of that. For each combination, we pair them with one realization that comes from the white noise, and as you see here, we are doing that realization for 5 seconds, and we consider the sampling rate of 0.1 second, 0.01 second, and that is fixed. Someone can use another one. Then for each of them, we run the finite element, we generate out quantities of interest, and then we use those pairs to train our model. Then for testing, we consider different cases. For example, here I'm showing the case that again, we have another set of VS and theta plus the synthetic time histories that now are going to change between 20 to 50 seconds, and we want to predict the response under that. So here is some of the results that we got. First of all, I'm showing the prediction accuracy when we have a synthetic plane base, but the duration can be way longer than what we have used for training. And for checking the accuracy of our model, we use the metric, the coefficient of determination, or R square. And here you see the histogram of this coefficient computed for 2,000 predictions that we have done under different white noises with different duration. And I'm showing on figure B and C 2 cases of doing the prediction as a good case and poor case. And you see that for the good phase, we have a very good agreement with the finite element result, and for the poor one, which is one of the, the limited cases that we had, still, we are in phase with the finite element results, but not necessarily capturing the actual amplitude. And if you take a look at the value of the displacement response in this bad case, you see it's significantly small. But for higher values, we are doing good performance. Then as a second step, we consider a set of earthquake plane waves, 14 of them, that is listed here at different stations for different events. And also, here is the range of the PGA that can change, and different durations and dominant frequency. And we wanted to see how this model is doing in terms of predicting the response under these earthquake plane waves. So we again use the R square value and compute that for all the predicted response at the different locations over the buried structures, in total, we had 14 earthquakes, 40 locations, therefore 560 predictions that we did. And in figures A and B, I'm showing some examples of predictions that we are doing. Again, as I said, we are training for, let's say, 1 or 5 seconds synthetic data, but now we are predicting the total response of the tunnel under earthquake time histories. And if you remember, I mentioned something about the amplitude. We wanted to see how the results perform for different range of the amplitude we have. And here in figure D, you see that for the cases that we have a smaller R-square values, those are the cases associated with a smaller amplitude. And one way to tackle this problem is to train a model, maybe one for horizontal displacement and the other one for the vertical one. And why this is the case is in many cases that we have vertically propagating shear waves, the majority of the response is just horizontal and the vertical displacement is quite small, and therefore the model has difficulty in predicting them. But with separating them, we should be able to improve the accuracy. So this is the model that we developed, and we check the performance under different types of excitation. And then we wanted to see how we can use it for different applications. So the first application is forward uncertainty quantification. Let's say we want to get the distribution of the horizontal displacement, the maximum horizontal displacement at different locations from P1 to P6. So as a first step, we wanted to do that by using our finite element method. So first we decided to only use 30 samples to generate the distribution, and the reason for choosing 30 was because we used the same number to train our model. And in the red histogram is the one we are getting from those analyses. Then we wanted to see if these are the real distributions that we have, so we increased the number of simulations to 1,000, and then we have the green ones, which at some of the locations are quite different. So we assume that the one that comes from 1,000 simulation is the reference distribution that we want to achieve. And then as a second step, we wanted to get a distribution by using the proposed surrogate model. So for that, of course, we didn't have any limitation to run many analyses. And after running lots of predictions, now we are recovering a distribution which is quite similar to what we can achieve by doing the finite element analysis. But in terms of the speed up, by doing this, we could achieve more than 2 orders of magnitude speed up in predicting the distribution. So as I said, one may think that, okay, now that I have, let's say, the displacement at point P1 and P4, I can subtract them and get the racking displacement time history. So we tried that as a first step, and here you see the difference that we are getting from a finite element and from the surrogate model, but not necessarily that prediction is accurate anymore, because the error that comes in predicting each displacement can add up and result in more error, especially when we have very small displacement. But one can use the racking displacement as a feature to train the model, and if we do that, we can resolve this issue. So here, for example, I'm showing the case that now we are using the racking to train that surrogate model, and if we do so, then if, for example, we want to have a distribution of maximum racking displacement considering different angle of incidence and shear wave velocity, now we can successfully capture that distribution compared to finite element method. So that is one example to show how we can use this model to accelerate some of these UQ tasks. And the other one is if we want to do some sensitivity analysis. So in this case, we wanted to consider some nominal values for VS0, K, angle of incidence, and let's say the burial depths. And then we want to see what happens if we change each of these parameters. And for that, we are considering, at the first, we consider only one excitation, and then we said that what if we run it under all 14 earthquake time history that we have. So if we wanted to do this by finite element analysis, we needed to run 3,500 cases, but we wanted to do that with the surrogate model to make things fast. So here, in figure, for example, B, what I'm showing is the dotted line is the prediction that comes from the surrogate model for the case that we are changing a VS0 from 50 to 200, but keeping the other parameters to be their nominal value. And I'm considering the earthquake number 14 for that case. To check how accurate the results are, we run the finite element model as well, and these cross dots are showing the results that comes from the finite element, which shows the accuracy of our model. After doing that, then we did the same thing for all the 14 earthquake time history we had, and the red line here shows the variation, the average variation that comes from those 14 time histories, and also this blue shaded area shows the case of having the mean plus minus 1 standard deviation. Also, the gray region shows the case that we have the envelope of the minimum and maximum racking displacement, considering all cases that we have. And this is just one example to show how we can speed up things, but as you see here, for that specific case, the racking displacement seems very sensitive to the value of the shear wave velocity at the surface and also the burial depth, but it's going to be least sensitive to other 3 parameters that we have. And I think that that's it. Just to conclude, so we have proposed the surrogate model based on LSTM, and it seems successful to predict the response of buried structures we consider under actual earthquake plane base, although we have trained that for very short duration synthetic data. And in all the studies that we have done, we noticed that we can achieve a speed of more than 2 orders and even reaching 3 orders of magnitude in many cases. And with that, I want to thank you everyone for your attention.